Hi, welcome back to my third and final video, this one on black holes. Ooh, spooky. Black holes have been a staple of science fiction for many years. I think they fill much the same niche as whirlpools do in maritime stories, reaching all the way back to the ancient Greeks. They're an inescapable force of nature that will suck you down and swallow you without a trace. But are they really that dangerous? Well, yes. But they are bound by the same physical laws as everything else in the universe. They're not magical, they don't get to break the rules. They give the appearance of bending some of them, but they're prone to a lot of misconceptions. For example, I've been asked by more than one person who had discovered that there is an exceptionally large black hole in the centre of our Milky Way, if that's the reason for the spiral shape of our galaxy, that we're all swirling down the plug hole and given enough time it's going to eat us all. Well, no. So to begin with, I'm going to show you how gravity works and applies to every object in the universe. This is Isaac Newton's law of universal gravitation. Don't worry, there won't be a test, but this is the equation used to calculate the gravitational force exerted by any object. And this term here says that to get the force we need to divide by the square of the distance to the centre of mass of the object. You'll recall that in the first video I said that was something important to remember, and here we are. It means that gravity is one of a class of laws called inverse square laws. There are similar ones for light and sound and anything else that radiates out in all directions. An implication is that force drops off quite quickly the further away you get from the object. Here on the surface of the Earth, we're 6,400 kilometres from the centre, so if we travel 6,400 kilometres into space, doubling the distance, we'll feel 1/4 of the gravitational force, 3 times 1/9, 4 times 1/16, and so on. In an example that's counterintuitive to a lot of people, if we replaced the Sun in the centre of the solar system with a black hole of the same mass, we would be the same distance from the centre of mass, and so we would feel the same gravitational force. The Earth would continue in its orbit, not even noticing. We'd all freeze to death. I'm not saying it would be a good thing. But the point is that a little bit of distance goes a long way towards making you safe. Now the converse of this is true if you decrease the distance to the centre, by which I don't mean drilling a hole down to the centre of the Earth means that gravity will increase as you drop down it, because there's lots of mass above you now. If we increase the density, making the object smaller, then the gravity will increase. If we make it half the radius, then 4 times the gravity. 1/3 the radius, 9 times the gravity. And it starts stacking up quite quickly, which means that if you get extremely dense objects, they've got phenomenal gravitational pulls at the surface. A white dwarf has about 150,000–160,000 times the Earth's gravity. Neutron stars have something like 10 trillion times the Earth's gravity. And black holes are just truly frightening. The gravitational pull determines the escape velocity from an object. Using Isaac Newton's example of firing a cannon, if the velocity is low, the cannonball will fall to Earth quite quickly. The faster it goes, the further it will travel, until at a certain critical velocity it will circle all the way around the Earth without falling, and you will be in orbit. If you travel a little bit faster than this, then it will escape, never to return. So a black hole is called inescapable because at a certain distance from it, the escape velocity is higher than the speed of light, meaning that not even light can escape from it. And given the fact that we know from the theory of relativity that nothing can travel faster than the speed of light, this means that nothing can escape from it. The basic concept of stars too large for light to escape from is actually a surprisingly old one. An early and rather underappreciated scientist, John Michell, came up with the idea in 1784. He called them dark stars. When he did the calculations to work out how large they were, however, he used the density of our Sun, making them impossibly huge. He had no reason to believe that superdense objects existed. In 1915, Albert Einstein revealed his general theory of relativity, and less than a year after that, the German physicist Karl Schwarzschild used relativity to make the calculations that form the basis of our modern understanding of black holes. Regrettably, just a few months after that, he died on the Eastern Front of World War I. His equations allow us to determine the Schwarzschild radius, which is the distance from a black hole at which the escape velocity equals that of light. The actual black hole itself is smaller, much smaller. There is nothing physical at the Schwarzschild radius, but the sphere defined by that radius is called the event horizon of a black hole. From within that volume, no information can escape. It is all unknowable. And so the event horizon is usually what is considered the physical extent of a black hole. So using my cherry tomato, if this was the event horizon of a black hole, it would have a mass equal to the entire Earth. Stellar mass black holes are obviously larger. For something the size of our Sun, the radius is about 3 kilometers. Now, while Einstein respected Schwarzschild's work, he and other scientists like Arthur Eddington did not believe that black holes were objects that could physically exist. It seemed to produce nonsensical results, that something could be crushed beyond the point of any force being able to resist it. And yet, just as Chandrasekhar showed that there was an upper limit to how large white dwarfs could get, beyond which electron degeneracy pressure could support them, there is a similar limit for neutron stars, calculated by 3 scientists, and this is known as the Tolman-Oppenheimer-Volkoff limit. One of those names is of course more famous from another area of physics. J. Robert Oppenheimer was the head of the Manhattan Project and so-called father of the atomic bomb. He kept busy. He did other things apart from that. Their calculations have been tweaked somewhat since they first made them. Modern consensus is that above about 2.17 solar masses, the neutron star can no longer support itself. Beyond that point, there is no known physical force that can stop the collapse. With our current understanding of physics, this leads to some odd results. It seems that in the center of a black hole, it diverges to infinity, infinite density, 0 dimensions with mass, what's called a singularity. A lot of physicists believe that this is just due to our incomplete understanding, that with something like the pursued quantum theory of gravity, we will discover there is something that stops this divergence to infinity. So-called stellar mass black holes arise when exceptionally large stars above about 30 solar masses explode in supernovas at the end of their life, just like the ones that give rise to neutron stars, except that the cores keep collapsing to form black holes. Now, how, might you ask, do we discover these dark objects that swallow light? Well, in 1964, a balloon carried an X-ray telescope above the Earth's atmosphere and found the first ever stellar mass black hole. Cygnus X1 is a binary system with one of the components being a black hole, and similarly to how I described that white dwarfs in binary systems can pull matter off their companion, so too does Cygnus X1. This matter spirals down toward the black hole, and as it spirals in, it heats up very, very high temperatures to the point where it emits beams of X-rays, and it's that X-ray signature that the telescope detected. Now, to be fair, this is still ever so slightly conjectural. There are a number of these so-called close contact binaries, and some of them are very clearly neutron stars, also pulling material off their companion and emitting X-rays. But there are a number of signatures that are characteristic of neutron stars, and certain close contact binaries do not exhibit those signatures, and the only thing that we know of in theory that could account for this is that it's a black hole. There is another class of object for which there seems no explanation except that they be black holes. These are the supermassive black holes found in the center of most galaxies. They are not stellar mass by any stretch of the imagination. They range in size from tens of millions up to billions of solar masses. And the reason we think they must be black holes is because that mass is concentrated into very small areas. we have good enough views of the center of our Milky Way to be able to observe stars in close orbit around Sagittarius A star, the central object. By measuring the speed of the star's orbits, we can calculate A star's mass. By seeing how close they come, we can place upper limits on the size of A star. It is so massive and so small that it is now considered conclusively proven that it must be a supermassive black hole. Now, last year there was a rather exciting development in which a consortium of astronomers managed to obtain the first ever direct images of a black hole in another galaxy. And I can think of no better way to round out this video than with this absolutely astonishing view down the throat of oblivion in the center of a galaxy over 50 million light years away. Our knowledge of black holes is still in its infancy, but with tools like this at astronomers' disposal, we can only imagine what sort of discoveries lie ahead of us. So that brings us to the end of my video series on some of the exotic and terrifying objects that we share our universe with. I hope you've enjoyed it. Thank you.